Okay, guys, this is the first video in two videos that I'm going to make on related rates. Um, this first video is going to be me talking about a couple of things that I need to make sure everyone understands before you do a related rate problem. So I'm not going to do any related rate problems in this video. They're all going to be in the second video. But in this video, I basically want you to understand the idea behind related rates first. So make sure you watch this video first, right? Watch the whole thing, and then you can see me solve related rate problems in the second video. All right, let's get started. So the first thing I want to talk about is I want to just mention, I have a couple of comments on implicit differentiation. This section is going to be all implicit differentiation. So I really want to make sure you guys are understanding that and also understand it in the context of what we're going to do in the related rate section. So first of all, suppose I ask you to take the derivative of the following function. Okay, so let's say I want you to find the derivative of this. Well, I'm giving you the entire function, so you know how to take the derivative of it. So I'm just going to put brackets around it and say that I want the derivative of this function. Okay, so it's a composition of functions, so you're going to have to take the derivative by using the chain rule, because there's an inner function and an outer function. This is the inner function, whatever's inside the parentheses. That's what we call stuff. So it's stuff squared. So I take the derivative of stuff squared. It's 2 times the stuff. So it's going to be 2 times the stuff. Okay, 2 times the stuff times the derivative of the stuff. And that's how you would take the derivative of this function. The point is, in this example, I've given you the formula for the entire function. And I know we would continue, but I'm not going to continue finding the derivative here. But here's what I want you to think about now. If I give you the formula for the entire function, no surprises, just here's the formula, find the derivative, you can find the derivative. If I don't give you the formula at all and I say find the derivative, you're going to be like, well, how do you do that? You haven't given me anything. Implicit differentiation is kind of like somewhere in the middle. It's kind of like I give you part of the formula, but I don't give you the entire formula. Part of the formula is going to be hidden from you. And if that part is hidden from you, can you still find the derivative? Maybe you can't write the entire formula down, but can you write something down as far as the derivative goes? In this problem, what I'm thinking of is the stuff that I've written in red. Imagine that wasn't given to you. So at this part of the problem here, if you're looking at this, the stuff in red, imagine it wasn't given to you. So instead of it being x plus e to the x minus sine x to the power 2, imagine only the power 2 was given, but the stuff inside the parentheses wasn't given to you. So I'm kind of saying, imagine this was hidden from your view. So you still see part of the formula. You know it's something squared. You just don't know what the something is. Well, then what's the answer? You can still figure out the answer. Just you can't give me the entire formula all in terms of x. It's stuff squared. The derivative of stuff squared is 2 times the stuff, so this would still be hidden from your view. But that would be, whatever I'm scribbling here would be the same as what I scribbled over here. And times the derivative of that stuff. That's the idea. So let me say the idea again. I want you to find the derivative of a formula when part of the formula is hidden from you. Okay, so if you look at this side here, I'm still giving you something. I'm giving you power 2. So it's something to the power 2, but I'm not giving you what that something is. Well, I could write down something squared. Or I could write stuff squared and say find the derivative of this. You're going to say, wait a minute, I don't know what the stuff is, or I don't know what the something is. But you can still say something about the derivative. You can say that, like for example, the derivative of stuff squared, you can still say it's 2 times the stuff, even though I don't know what the stuff is, times the derivative of the stuff. And you say, Greg, that's as far as I can go. And if you tell me what the stuff is, then I can tell you the whole exact answer. Otherwise, that's as much as I can tell you. That's basically what implicit differentiation is doing. What they're going to do is, instead of writing something or stuff, instead of writing a word like that, they're going to use another letter. So in the implicit differentiation section, x is the variable. And so if you see any other variable, think of it as it's really me hiding a bunch of stuff with x's in it. So basically the problem that's up there on the top, instead of me scribbling out all the stuff in the parentheses, I'm going to call it a y. It doesn't have to be y, but in the implicit differentiation section, it's a y. So it's like I'm asking you to find the derivative of y squared. You have to not think of y as a letter, as a variable. You need to think of it as y is really stuff with x's that we don't know. If I would have known what was back here, then I would know what y is. So when I ask you to find the derivative of y squared, it's really stuff with x's squared. That stuff with x's, though, is being hidden from you. And I'm still asking what the derivative is. Okay, and to find the derivative, you say, well, I guess I don't really need to know what the formula for y is. I don't need to know what that x's stuff that's being hidden from me is. I can still say something, because chain rule says when you take the derivative of stuff squared, it's 2 times the stuff times the derivative of the stuff. So the derivative of this is 2 times the stuff. Since I don't know what the stuff is, we keep it as y, times the derivative of the stuff, y prime. Okay, so that's the idea. Let me say it one more time. We're trying to find the derivative of a formula when the entire formula is not given to you. Part of it's given to you, and part of it's hidden from your view. The part that's hidden in the implicit differentiation section, we'll use the letter y for that. Okay, so x will be the variable. I call that, well, x is what we're going to use for the input of the function. It's what I'm going to call the independent variable. When you take the derivative of something involving x, it's the regular old derivative, but when you take the derivative of something involving y, don't think of y as a variable. Think of it as the part of the formula that's hidden from you. Okay, so even though I've written all this, it's like, well, what is y still? I don't know, but I could still write down the derivative. Okay, so you're trying to find the derivative of something when part of the formula is hidden from you. The part that's hidden from you, we're going to call it y. And still we can write down what the derivative is. So you tell me, okay, it's this. And you're like, but wait a minute, I don't know the answer because it should have x's in it. And you say, well, tell me what the hidden stuff is, and then I'll tell you the rest of the answer. Otherwise, that's as far as you can go with the answer. At least that's how implicit differentiation works. Let me do one more quick example on that. So I'll just give you another one where some stuff is hidden from you. So let's say, for example, I wanted to find the derivative of sine. In other words, sine will be the part of the formula I'm going to give you. But there's stuff inside it, but I'm not going to tell you what it is. So since I'm not telling you what it is, I'm hiding it from your view, I'm going to call it y. So I'm asking you to find the derivative of this. When you see this, you need to be thinking that it's sine of, and then inside the parentheses is a bunch of stuff with x's that is hidden from your view. They're not telling you what it is. So they're writing a y. And you're going to be like, okay, well, since part of the formula is hidden from me, I'm not going to be able to get the whole entire answer in terms of x, which is what I would like, but I can still write something. We know, again, we're going to use chain rule here because this is sine of stuff. So the derivative of sine of stuff is, it's going to be cosine of the stuff. Again, it's unfortunate I don't know what the stuff is, but I can still write y. It doesn't matter what it is because whatever it is goes inside this parentheses. So it's cosine of the stuff times the derivative of the stuff. And that's as far as you can go unless someone says, okay, I'll tell you what y is now. Y is, x squared plus e to the x. Then you're like, okay, then it's cosine of x squared plus e to the x times the derivative of x squared plus e to the x. But if they don't tell you what y is, this is as far as you can go. Okay, another thing about the implicit differentiation section is that in that section, x is the independent variable. Okay, so let me write this down. So in the implicit differentiation section, x is the independent variable, which means the input, and y is the stuff that's hidden. In other words, y is stuff with x's, but it's unknown. So we're just going to write y. That's what happens in the implicit differentiation section. Now, in the related rates section, which is what we're supposed to be talking about today, the variable is not going to be x. The variable is going to be t. Okay, time to erase. So the independent variable is not an x. The independent variable is t. So let's go ahead and write that down. Sorry, a lot to erase here. Okay. So in the related rates section, t is the independent variable, which means the input. Another way to say it is when you take the derivative of something that has a t in it, you take the regular old derivative. Okay, but if you see any other letter at all, it is the stuff that's hidden from you. So once again, part of the formula is going to be hidden from you. And instead of me writing the word stuff or something like that, I'm going to use a letter. Even x, so that might get a little confusing. So x, y, r, theta, any other letter is the hidden stuff. And that stuff involves t's. Hidden stuff involving t's. Okay, so let me say that one more time. T is the variable in the problem. So if I ask you to take the derivative of x squared, it's not 2x. In the implicit differentiation section, it would have been 2x. But in this section, the derivative of t squared is 2t. But any other letter, think of it as stuff. So x squared, you need to think of that as stuff that's hidden from you squared. And that stuff that's hidden from you is involving t's. Okay, so that's the story there. So we're changing from x as the input or independent variable to t as the input or the independent variable. Okay, also one more thing is we're going to stop using the prime notation in this section, because when I use the prime notation to indicate derivative, it's actually a little bit confusing, especially when you forget what's the letter we're taking the derivative with respect to. So instead of using this for differentiation, this is going to mean the derivative with respect to t. So I'm going to be using d dt for this section. If you use the prime, it's not the end of the world, but the point is that when you use this other notation, the bottom letter lets you know what the letter is in the problem. So if I ask you to find, like if I ask you to find the derivative of x squared and I write it like this, then you're going to be like, well, wait, what section am I in before I can answer this question? Am I in the related rate section? If I am, then it's not 2x. If I'm in the implicit differentiation section, then it is 2x. So that gets confusing. But if instead of using that notation, we use this notation, so instead of this, let's say I use this, now you know that x is the variable and the derivative is 2x. Whereas if I write something like d dt of x squared, now you know that x is not the variable, so you don't just go ahead and write 2x. Okay, so we're going to be using this notation in this section. Okay, so let's just summarize these notes here. Okay, so I want you to think of implicit differentiation as a way to find the derivative of a formula when part of that formula is not given to you, when part of the formula is hidden from you. So they give you some part of the formula, but not the whole thing. And even so, some part is hidden from you. Can you still write down what the derivative is? Your final answer will not be complete in a sense because you won't have, since some stuff is hidden, your answer is going to be in terms of the stuff that's hidden. That's the idea. Okay. In the related rate section, all functions are function of time. Okay, so they're functions of time. Time is the input, time is the independent variable, not x, which is what it normally is. Okay, so what that means is t is going to be the independent variable in the related rates section. If you see any other letter, even x, I know the x one is going to be confusing, but any other letter, x, y, theta, any other letter besides t, I want you to think of that as stuff with t's in it, but it's hidden from you, so no one's telling you what the formula is. So x, if you see an x in a problem, x is really some stuff with t's, like t squared plus e to the x, I don't know, some formula, but they're not telling you what the formula is. So x is a formula with t's in it, and it's hidden from you. Y is a formula with t's in it that's hidden from you. Any letter other than t is a formula with t's in it that's hidden from you. All the derivatives are going to be with respect to t. So again, if you're taking the derivative of something that has t's in it, it's the regular old derivative. But if you take the derivative of anything else that doesn't have t's in it, then it's going to, that stuff, any other letter, is going to be stuff with t's in it. You're going to have to use chain rule, that kind of thing. Okay, so that's what it says here. When you take the derivative of anything that involves a letter other than t, you're going to have to use a chain rule. Okay, so now I want to practice taking derivatives of things that you might see in this section. Notice, so I'm going to use the prime notation sometimes, and sometimes the DDT notation, but I want you to know that in my final answer, I'm always going to have the DDT notation in it. Okay, I probably shouldn't be using primes at all, but primes are bad because they don't tell me what the variable is. All right, let's look at this example. Take a look at the three parts here. The first part is asking for the derivative of t squared, and then the derivative of y squared, and then the derivative of x squared. What's the difference? Basically, if it's a t, you take the regular old derivative. Because it says ddt here, okay, so that means t is the variable. T is the independent variable in this section. So that means when you take the derivative of something involving t's, it's the regular old derivative. When I say regular old derivative, I mean no chain rule, nothing's hidden from you, anything like that. So the answer to this one is 2t. That's the end of the story. Now, I do want to be honest here. In the related rates section, you're actually never going to see the letter t. Okay, but I still want you to understand that if for some reason you did see the letter t, then it's the regular old derivative. Okay, what if we take the derivative of y squared? Remember, y is really a formula with t's in it that's hidden from you. So this is stuff squared, and to take the derivative of this, you're going to have to use a chain rule. So the answer is going to be 2 times the stuff, 2 times the stuff, times the derivative of the stuff. Now, I know normally we'd use a y prime here, but I don't want to use y prime because the prime notation sucks, because it doesn't tell you. It's a fast notation. That's good about it. But the thing that sucks about it is it doesn't tell you what the variable is. So instead of writing y prime now, I'm going to write dy d, what do you think? If you're thinking x, don't forget the variable is t. So it's going to be dy dt. So instead of 2y prime, so instead of writing the y prime, you're going to write dy dt. Okay, let's try this one. This last one may be confusing because we've been so used to seeing x as the variable in the problem. But in the related rate section, I can't stress it enough, t is the variable. So this is really stuff with t's squared. The stuff with t's is hidden from you, and so they're calling it x. So it's just like part B. Okay, this is stuff squared, and so the derivative of it is going to be 2 times the stuff times the derivative of the stuff. So I need to say the derivative of x. Don't say x prime. What are we going to say instead of x prime? You're going to write dx dt. Okay, in this section, it's always going to be d something dt. Okay, because t is the variable, and then you just put the x up on top. So that just says derivative of x with respect to t. Okay, let's do more practice. Okay, here I use the prime notation. Okay, but again, same thing. We're taking the derivative with respect to t. It's just, if I put this on the final or something and asked you this question, you'd be like, I don't know how to do it because you got to tell me what section it's from. But right now, we're in the related rates section. So that means t is the variable. So we take the derivative of something involving t, it's the regular old derivative, and this has just t's in it. So the derivative of cosine t is negative sine t. Story's over. No chain rule. Nothing's hidden from you. There's no stuff, nothing like that. But now it's cosine x, the derivative of cosine x. So remember that x, what is that stuff? What is x? X is the stuff that's hidden from you. This is cosine of a bunch of stuff with t's in it. Okay, that's what x stands for, stuff with t's in it. But I don't know what it is. It's hidden from you. Still, we can write down something about the derivative. So you know that it's cosine of stuff. So the derivative of cosine stuff is negative sine of the stuff times the derivative of the stuff. And again, instead of writing x prime, we're going to have to write the derivative of x like this, dx dt. I want you to understand that this answer that I've just written down here has t's in it. You don't see them anywhere. They're there, though. They're just hidden from you. Right here. That is a bunch of stuff with t's in it. So keep in mind that x is a formula that has t's in it. You just don't know what it is. Okay, but it exists. It's some formula. And then you take the derivative of that formula here. So this really, in the end, is just a bunch of stuff with t's but I can't write it down because I don't know what that formula for x is. Same thing here. This, if you were to calculate what that derivative is, it would just have t's in it, but you can't calculate it because x is hidden from you. So that's as far as you can go. Okay, let's go to this next one. So it says cosine theta, but the story is the same. Theta, if you don't see a letter t, if you see any other letter besides t, then it's stuff with t's in it. So this is cosine of stuff with t's in it. Okay, just we don't know the formula, it's hidden from us. So it's going to involve chain rule again. It's cosine of stuff. The derivative of cosine of stuff is negative sine of the stuff. So negative sine theta. That theta looks weird. Okay, negative sine of theta times the derivative of the inside, the derivative of theta. We're going to write d theta dt. Okay, no primes in this section. We're going to write it like that. Okay, let's practice a little bit more. Okay, so once again, we're going to take the derivative of square root of t for the first one. And again, t is the variable. So when you take the derivative of something involving only t's, regular old derivative. The derivative of square root of t is 1/2 square root of t. Regular old derivative. No chain rule. But for the second one, remember, y is stuff with t's in it that's hidden from us. We don't know what it is. So it's going to involve chain rule because it's square root of stuff. So the derivative of this is 1/2 square root of stuff times the derivative of the stuff, and the way you're going to write that is dy dt. Okay, let's try the next one. Same thing, it's an x. Don't get confused when you see an x. In the related rate section, x is not a variable. X stands for stuff with what in it? Stuff with t's in it, because t is the variable in this whole section. So this is square root of stuff, even though the stuff is hidden from us. So the derivative of square root of stuff is 1/2 square root of stuff. So it's going to be 1/2 square root of x times the derivative of that stuff, which is dx dt. Okay, a couple more examples. Okay, so again, I'm using the prime notation, but just remember it as d dt. We're taking the derivative with respect to t. Or another way to say it is t is the independent variable. When you take the derivative of something involving just t's, it's the regular old derivative. If you take the derivative of something involving any other letter, it's going to be stuff that's hidden from you. And pretty much always you can use a chain rule for that. Okay, so the derivative of secant t, since it has a t, regular old derivative, it's going to be secant t times tangent t. So that's the end of the story on that one. But when you take the derivative of secant x, x is stuff with t's in it that's hidden from you. So it's stuff, it's going to involve chain rule, and the derivative is going to be secant x times tangent x. So secant of stuff, tangent stuff, times the derivative of the stuff, which is dx dt. Okay, let's do the last one, derivative of secant theta. Again, theta, you have to think of it as a formula with t's in it that's hidden from you. So even though it's hidden from you, we want to still write down the answer, even though we won't be able to write the answer involving all t's because I don't know what theta is in terms of t's. But still, this is secant of stuff. The derivative of secant stuff is secant stuff times tangent stuff from the chain rule. But then chain rule says, okay, then you have to do times the derivative of the stuff. So the derivative of theta, but don't write theta prime, write d theta dt. You always put a dt on the bottom because t is the variable. On top you put d, whatever the thing is that you're taking the derivative of. Okay, so those are the kind of things we're going to take the derivative of in the related rate section. Okay, that's the first thing, implicit differentiation, how to think of it, and just don't forget that t is the independent variable in this section. Okay, so now we have the second thing I want to talk about. Okay, so now we're going to talk about functions of time. Whenever a quantity is changing, that quantity is a function of time. Let's look at a few examples. Okay, so we're going to look at an animation right now, and this palm tree that you're seeing is going to grow. Okay, so its height right now, it's kind of small, but then it's going to grow. So let's go ahead and watch it real quick. And as it grows, you can see that the height is getting bigger and bigger and bigger. So the height is changing. Because the height is changing, it's a function of time. So when I say the height's a function of time, I mean there's a formula for the height. Okay, so we don't know what it is, but the height can be written as a function of time. Let me just make up something. It could be something like t squared plus 5t. I totally made that up. I don't really know what the formula for the height is. All I'm trying to say is if it's a function of time, since the height is changing, it's a function of time. That means you can write a formula for the height, and the formula for the height will have t's in it. There'll be a formula with t's in it. And so the point is, now you can tell me what the height of the tree is at any moment by plugging in a number. So there's a formula for the height with t's in it. If you plug in a number for t, you'll get the height at that moment. So for example, if I want to know the height of the tree 2 seconds after it starts growing, you would plug in 2, and you'd get whatever you get when you plug in 2. Again, this doesn't really matter because I don't really know what the actual formula for t is, but let's say it's 14 feet or something. Okay, if I want to know the height at a different time, you plug in a different number. So if I want to know the height in 5 seconds, then you could plug in 5 to get the height, which you get 50 feet. I know in real life, palm trees don't grow that fast. You know, it doesn't go from 14 feet to 50 feet in 2 seconds, but, you know, I didn't even specify what the units are. So this could be years, you know. So after 5 years, it could be 50 feet tall, but after 2 years, it could be 14 feet tall, that kind of thing. So when I say the height is a function of time, I mean there's a formula you can write for the height where the formula has t's in it. So there's a formula for height that has t's in it, and if you plug in a number for t, you'll get the height at that time. So another way to think about it is that there's a formula. So the height is a function where the inputs are time and the outputs are going to be the height at that time. Okay, so that's what I mean when I say that the height of the palm tree is a function of time. I mean there's a formula for the height that involves t's, and then you can find the height at any moment by plugging in the time. So inputs are time, outputs are the height. So if you say, I want to know the height at this time, you plug in the time to the height function, and you get the height at that time. Okay, so now that we have that the height is a function of time, there's other things too. Whenever you have a function of time, the derivative means something. So the point is, the height is changing, so I want to know how fast is it changing, or how fast is it growing. That's the idea. It's called the rate of change. Since the height is changing, I want to know the rate of change. The word rate, it can have two different meanings in a math class, but basically in our class it means how fast is a thing changing. So rate of change, in this problem anyway, would mean, so how fast is the height changing? In other words, how fast is the tree growing? And the derivative will tell you that. So whenever you have a function of time, if you take the derivative tells you how fast the thing is changing, but you do have to plug in a number first. So you get this by the derivative. So the derivative of the height is the rate of change of the height, but you have to plug in a number. So that's very important. So if I say, how fast is the tree growing? I can't answer that question. But if I say, after 2 years, how fast is the tree growing? Then you would be looking for h prime of 2. Okay, so if you plug in a number to the derivative, it'll tell you how fast the tree is growing at that time. Okay, let me go ahead and erase some stuff here. Now I'm erasing a formula for the height here that I just made up. In related rate problems, we're actually not going to know the formula. But just because we don't know the formula doesn't mean there isn't a formula. So let me make sure we're clear on this here. So the height is a function of time. So the height here, the inputs are times and the outputs are heights. But if you want to know how fast the thing is growing, that would be the derivative function. You would plug in a time, and the output would be how fast is it growing? How fast is the tree growing? Or how fast is the height changing? Okay, so height function, how fast is the height changing? But remember, functions don't really tell you much until you plug something into them. So if you want to know the height, you don't just look at the height function. You have to plug in a time to it, and then the output will be the height at that moment. And then if you want to know how fast the tree is growing, well, it might be growing really fast certain times and other times slowing down. Maybe in the summer it'll grow faster and in the winter it'll grow slower, something like that. So if you want to know how fast the tree is growing, same thing. You find the derivative, but the derivative alone doesn't tell you how fast it's growing. You have to plug in a time to it, and then the output will be how fast it's growing at that time. Okay, one more thing I want to tell you about functions of time is that if the thing is increasing, then the derivative will at that time will be positive. Okay, so let's write that down here. So if the height is increasing, then the derivative at the time that you plug in, so let me just put question mark here or something, but you plug in some time, will be positive. So the derivative is positive if the thing is increasing. In this case, if the height is increasing. If the height is decreasing, the derivative at that time is going to be negative. Okay, so again, I talked about basically 5 things here. One more time. The height is changing, so it's a function of time. The height is a function of time. That means there's a formula for the height that involves t's. We may or may not know that formula, but there is a formula. Most of the time we don't know it. So that's the first thing. Second thing, if you plug in a number into the height function, it'll tell you the height of the tree at that time. Okay, so remember, if you don't plug in a number, you just have some formula. But if you plug in a number for t, if you say, I want to know the height at this time, you plug in that number for t, and you get the height at that time. The next thing is the derivative. The derivative is going to tell you something about how fast the thing is changing. So you take the derivative, it's called the rate of change. Take the derivative, but it'll give you the rate of change of the height, but you have to plug in a number first. So if you say, how fast is the tree growing? You have to first plug in a number and say, oh, how fast is the tree growing after 5 years? Then you plug in 5 years to the derivative, and that'll tell you how fast the tree is growing. And then if you get a positive answer when you plug in a number for the derivative, that means it's, in this case, the height is getting bigger. So whatever quantity is changing, it's getting bigger. And if you plugged in a number to the derivative and you get a negative number, it means whatever it is, in this case, the height is getting smaller. I know in this example, it's growing, it's never getting smaller, but in other examples, the quantity we're looking for could be getting smaller than the derivative's negative. Okay, we're going to look at a few more animations. So let's take a look at this next one here. Okay, so here we have a skateboard, and basically the idea is someone's going to kick this skateboard. They're going to kick it and it's going to start moving to the right, or someone's going to push it and it's going to start moving to the right. Let's go ahead and look at the animation first. Okay, so the skateboard just went to the right. All right, now let's go ahead and look at the skateboard again. Imagine that there's like a wall or a reference point right here. I'm going to focus on one point on the skateboard, the tip here. Let's say the very end over here. That point is going to go to the right. So that point is changing. When I say that point is changing, the right way to say it is its position is changing. If I want to know where is the end of the skateboard, the tip of the skateboard, where is it means what's its position. Its position changes. Its position right now is whatever this distance is. But as it moves to the right, that position is going to get bigger and then bigger and then bigger. So I'm using this as a reference point, like a wall here. Okay, right here. So I'm saying what's its position compared to that. So its position is changing with time. So let me call the position S. So the position, we usually use S for position. The position of the tip of the skateboard. Maybe I should write front of the skateboard. Of the front of the skateboard is a function of time. Because it changes depending on what time you're looking at it, because the skateboard is moving to the right. So that means, what does that mean? There's a formula for the position. So there's some formula for the position. I don't know what it is, but it involves t's. It could be like, t cubed minus 2t plus e to t. I just made up a random formula here. I don't know what it is. All I want you to know is there's some formula for the position of the front of the skateboard that involves time. So it could be that, it could be something else, it could be unknown, which almost always is going to be unknown. Okay, but the way the position works, don't forget the position function is that the inputs are going to be time and the outputs are going to be the position at that time. So there's some formula, but the formula doesn't really help you until you plug in a number. So if I say, if I want to know where the front of the skateboard is at time 3 seconds, you plug in 3 seconds into the position function, and it'll tell you the position of the front tip at that time. So this might be at time, so at time 0 seconds, the position might be here, t equals 0. This might be at time 1 second. This might be at time 2 seconds. So if I want to know, what's the position, it would be here at time 2 seconds. If I don't know what that position is, basically I'm asking for this distance here, you'd plug in 2 seconds right here into the position function, and the output would be the position at that time. Okay, so that's the way the position function works. And then if you take the derivative of the position function, remember what that tells you, it's going to tell you how fast that front of the skateboard is moving. In this situation, it's going to be the velocity or the speed of this end of the skateboard. Think of it as the speed if you want. Okay, so that's what the derivative will tell you. Okay, so I'm going to go ahead and write some stuff here. So the derivative, what does the derivative tell you? It's going to tell you the rate of change of the front of the skateboard. But why am I saying rate of change? Because the position of this point here is changing. So the derivative will tell you how fast it's changing. In this situation, it's what's the speed of that in the skateboard. But again, it's really a formula until you plug in something. So you think of the derivative as a function. You plug in time, and the output will be this, I'll just write speed here, or velocity at that time. If you just kick a skateboard and you let it go down the street or whatever, its speed will change depending on, it'll slow down, eventually stop, that kind of thing. So when you say, what's the speed of the skateboard, I'm going to ask, well, at what time are you talking about? So if you plug in a time to the derivative, then the output will give you the speed at that time. That's the important thing. And the last thing is, don't forget that if you plug in a number to the derivative and you get an output, if the output's positive, it means something is increasing. In this case, as the skateboard goes to the right, this position, so the position starts there, then it moves to there. So the position, okay, so here's the original position, this length basically. Then the position goes to this. See, the length is getting bigger. So we expect that when you plug in a number to the derivative at any of these times, you're going to get a positive answer because its position gets bigger depending on time. Whereas if you would have plugged in a number and got a smaller number, it would have meant the skateboard's going that way. Like the position starts here, so this is the length of that, then the length gets smaller, that kind of thing. Okay, so you see, as we saw that animation, that it was going to the right, and the position was getting bigger, and that means the derivative, which is how fast the front end of the skateboard is going, you would get a positive number if you plug into that. So I want to look at it again. So here's a picture of the skateboard again. But now let's say I'm not interested in the front point. I'm interested in the back. Same kind of thing. Let me put like some kind of wall over here. So like a reference point where we measure positions. So this would be the position at the beginning. But then as the skateboard moves to the right, the position will change. Okay, so this dot will eventually move to the right. As it moves to the right, the position, maybe better to put the position down here. Position starts like that. Then later on, the position will be there. Then later on, the position will be there. This is where the left end of the skateboard will be as it moves along. It'll go more and more this way. So same kind of thing. The position of that dot is changing. So it's a function of time. So the position of the back end is a function of time. That means there's a formula for the position of the back end. When I say position, I mean position relative to the wall. How far is it from the wall? There's a formula for that position that has only t's in it. So for example, EG stands for example, the position of the back end could be something like 2t plus 1 or something. I just made up some random formula for it. But again, what you need to remember is that we have some kind of function here where the input is time and the output is going to be the position of the back end at that time. So since the position of the back end depends on changes, there's a formula for it that involves only t's. But the formula doesn't really tell you much until you plug something into it. If you plug in a specific value for t into this position function, then you'll get the position of the back end at that time. And then we're going to be taking the derivative, and the derivative is going to tell me how that position changes, which will basically be the speed of the back end. We talked about in the last class that the derivative of position is velocity. So it's kind of like the speed or the velocity of the back end. But again, it's a function where you plug t into it, and the output is going to be the speed. I'll write velocity this time. It doesn't matter. Velocity of the back end at that time. That's important, at that time. And when you do plug in a number to this, if you get a positive answer, it means the position is increasing. And in this case, we see the position is increasing because it starts from here. So that length is kind of like, no, sorry, it doesn't start there. It starts here. That's the initial position. Then later on, it moves to here. So that length is bigger. Then later on, it moves from here to here. So that length's even bigger. So the position is increasing. That means we expect a positive answer for that. And you can see as it goes that it's moving to the right like that. Okay, let's go ahead and look at another example of a function of time. So what I'm trying to show you here, so we have a sphere, and this black line that I'm drawing here is the radius of the sphere. And then I drew the radius, that radius again separately over here. And what's going to happen is this sphere is going to start getting bigger and bigger. You could think of it as a balloon. Someone is blowing up a balloon. So they're using their mouth to put air into this balloon, and this balloon's going to get bigger and bigger and bigger. As it gets bigger and bigger and bigger, things about the balloon get bigger. What gets bigger about this balloon? Lots of different things. Okay, so real quick, let's just watch this balloon get bigger. So let's watch as it gets air put into it. So see, it gets bigger and bigger and bigger as we're putting more air into the balloon, and it ends up like this. And again, the whole time you saw this radius here, and I drew the radius over here as well. Okay, so these two things have the same length. I just drew it separately over here. And now there's a few things that are a function of time. The volume is a function of time. The volume is changing. The volume of air inside the balloon is changing. It's getting bigger and bigger and bigger. So the volume is a function of time. So a function of time. In other words, remember, when I say something's a function of time, I'm really saying, well, there's about 5 things I want you to know once I say that. First thing I want you to know is that means there's a formula for the volume that involves t's in it. I don't know what the formula is. I won't write it down. But it'd be v equals and then some stuff with t's. And then the second thing is, once you have that formula, what does it tell you? Well, if you plug a number into it, time would be something you'd plug into it. The output would be the volume at that time. Okay, so, I'll go ahead and draw a picture for that. So you plug t into this volume thing, and it tells you the volume of air inside the balloon at that time. If you take the derivative of the volume, that would be another function of t, because you take the derivative of a formula with t's, you're going to get another formula with t's. And what does that derivative function tell you? Well, it's okay, so we have a formula for sure, but the important thing is if you plug a number into it, the answer will tell you the rate of change of the volume. So rate of change. Since the volume is changing, what I'm asking is how fast is it changing, and that's called the rate of change. So rate is like how fast is it changing. So rate of change of the volume at that time. You could think of it as a speed, but it's not like the other ones where you saw something traveling like a skateboard or a car, or like, think of the height of the palm tree. You could think of a car kind of driving or something like that. It's not like that. but it's how fast is the volume increasing. Okay, so that's one function we have going on here. What else is changing when this balloon gets blown up? Okay, so besides the volume being a function of time, the surface area is another thing that's changing. There's a lot of things that are changing. If you're like, what's surface area? Surface area is the area of the surface. In other words, if you took this balloon and wanted to give it as a gift to someone, so you're going to wrap it in wrapping paper, how much wrapping paper would you put around it? That would be the surface area. So I'm just going to write surface area is a function of time. That means there's a formula for the surface area that has only t's in it. Most of the time, we don't know that formula. Also know that that means that if you plug in a specific time into the surface area function, you'll get the surface area at that time. So remember, a formula is no good unless you plug something into it. Then it tells you something. So if you plug a number into it, it'll tell you the surface area at that time. So you're going to plug in a time into it. If I say, what's the surface area after time at time 5 seconds? You plug 5 seconds in, and you get the surface area at time 5 seconds. You want the surface area at time 10 seconds, plug 10 seconds in, you get the surface area at time 10 seconds. And then the next question will be something about speed. If you take the derivative of the surface area, remember what that tells you? It tells you the rate of change of the surface area, meaning how fast is the surface area changing. In this example, when we saw the animation, it was going kind of slow. So surface area wasn't changing very fast. But the point is, you want to know how fast? You got to plug in a number first. Plug a number t into it, and the output will be the, rate of change of the surface area at that time. How fast is it changing? Also remember that if the surface area is getting bigger, then you expect a positive answer for this. If the surface area is getting smaller, you expect a negative answer. So as far as the derivative goes, if whatever quantity is changing is getting bigger, you're going to get a positive answer for the derivative when you plug a number in. If the quantity that's changing is getting smaller, when you plug a number in, you're going to get a negative answer. What else is changing? Lots of other things. The diameter of the balloon. By the way, I called it a balloon. So, you can imagine a problem says you have a spherical balloon and you're pumping air into it or you're blowing air into it and, whatever. Or sometimes the problem will say you're blowing a bubble from some bubble gum. And for some reason, the bubble is in the shape of a sphere. That's kind of why I chose pink, by the way, to think of bubble gum. But whatever, bubble gum or a balloon or some spherical object that we're pumping air into it, and it stays a sphere the whole time. Okay, so back to what I had asked. What other quantities are changing? Well, the radius is changing. So radius, which is r. This length here, which is this length, that's a function of time. It is a function of time because it's changing. That means there's a formula for the radius that involves time. Again, I don't know what that formula is, but there's a formula for it. And if you take the, so that means if you think of the radius as a function, if you plug a time into it, you'll get the radius at that time. So for different times, you plug in those different times to the radius function, and you'll get the radius of the balloon or bubble gum or whatever at that time. Well, what does the derivative tell you then? The derivative will tell you how fast the radius is increasing at that time, but you have to plug a number in. So if you take the derivative of the radius, you're going to get another function of time. Okay, again, I may or may not know the formula, but there's a formula for the radius involving t. So if you take the derivative of that formula, whether you know the formula or not, there's a formula for the derivative of the radius that involves only t's. T is the input, and the output will be how fast the radius is changing at that time. If it's growing, if it's getting bigger, then you're going to get a positive answer there. Once you plug a number in for t, you get a positive answer here. If the radius is getting smaller, if we're letting air out of the balloon, for example, then we expect a negative answer when we plug into the derivative. Okay, I want you to look at the animation again. I want you to see, I want to compare this radius changing to a speed. So before I show you the animation, let me just explain that as the animation is going, I keep drawing this radius over here. I'm drawing it in such a way that this part of it, this point here, over here, is stationary. That point is not moving. So then this line segment is going to get bigger and bigger and bigger as we go. And if you focus on the right end of the line segment, it's basically, when I say how is the radius changing, I'm basically asking you how fast is this going? Okay, let's go ahead and look at the animation again. Okay, so one more time before we look at the animation, I'm drawing this radius over here in such a way that the center here is over here, not moving. And so we're just going to focus on this end. So you see, as the radius gets bigger, this end is going to go out that way. So this end here is going to move that way. So this end's stationary, this end is going to move that way. And as it moves, basically when I say what's the rate of change of the radius, it's basically saying what's the speed of this dot here. Okay, so let's go ahead and watch it. And you see, as you watch it, it's moving to the right, whatever the speed of that right end is, that's basically what I mean when I say what's the derivative of the radius, what's the rate of change of the radius. Now, of course, the speed may not be the same, may be different depending on what time how you're talking about, so that's why you have to plug in a time to it. Okay, let's go ahead and look at this animation one more time where I have it going faster. Okay, so same balloon kind of thing, but we're going to pump in air faster. And you see the balloon is growing much faster, the radius is growing much faster, surface area is growing much faster. But because they're growing, it's all positive. So the derivative of the volume is going to be positive if you plug in a number for t. The derivative of the surface area is going to be positive, and the derivative of the radius is going to be positive, because all of these things are increasing. Remember, if those quantities were decreasing, they'd get smaller. But not only that, not only are they positive, they're going to be much bigger than they were in the last example because they were growing slower in the last example. Okay, just for fun, let's watch that animation one more time. Okay, so everything is growing much faster. Okay, let's look at one more animation here. This is a very typical example of a related rate problem, even though we haven't done any related rate problems yet. This is just preliminary stuff. But here's a ladder resting against the wall. So this is a wall right here. That's what I tried to draw here, a wall, and this is the floor. Okay, this point here is going to always be in contact with the floor. This point here is always going to be in contact with the wall. But what happens is, imagine this ladder starts to slide down. Maybe the wall and the floor are slippery. Maybe someone kicked the ladder or something. This point is going to move this way. Now, I worked really hard on this animation, but was not able to get it perfect. So that point on the bottom here, you need to pretend is always in contact with the floor. It doesn't come off the floor, it doesn't go below the floor, but in the animation it doesn't exactly do that, but you're going to have to play a little bit of a game of pretend here. Same thing over here. This point over here is always in contact with the floor. It's going to be sliding down. Okay, it's going to slide down the whole time, but I know in my animation it may look like it came off the wall. It may look like it went behind the wall. I tried my best. So hopefully that makes sense. Just pretend this point goes down the wall the whole time. This point goes to the right the whole time. Throughout the entire animation, this point is always in contact with the floor. This point is always in contact with the wall. Okay, let's go ahead and look at this animation real quick. Okay, so you see it slides down, and this point finally went down to here. So it started up here and it went down to there. And this point here had started here somewhere and went sideways to that way. Okay, so we're going to look at positions real quick. Let me go ahead and look at the beginning of this here. So this point here, I want to talk about, because I want to talk about how fast it's going. So think of its position relative to here. Whenever you say position, you have to say position from where. You know, when we did position functions, I always said there's a rock on the side of the road or a tree on the side of the road. We want to know the car's position relative to this tree or rock. Same thing here. I want to know where this point is relative to this point here. This is where the wall and the floor meet. So here's the position at the beginning. As it slides down, this point moves this way. Let's say it ends up here. The position increases to this. Then let's say it finally ends up here. The position finally increases to this. So the position of this dot is increasing as it goes this way. Okay, so it's going that way. And so its position, therefore, since it's changing, is a function of time. So the position of the bottom, okay, so position of the bottom is a function of time. Once again, what does that mean if the position is a function of time? That means there's a formula for the position of the bottom, then it has t's in it. If you plug in a number to that function, you'll get the position at that time. If you take the derivative of the position, it'll tell you the rate of change or how fast the bottom is sliding, but you do have to plug in a number first. So I'll be like, how fast is it sliding at this moment? Then you plug in a number to it. So the position is the bottom, also the position of the top. Let's look at this point here. I want to measure its position relative to the same dot here. So that position, the initial position is there. As it slides down this way, let's say it goes to here. Notice the position is smaller now, or the length, I guess, from here to where we're measuring the position from is smaller. And then it keeps going down, position gets even smaller, and eventually it gets over here, position is 0 at that time. So if I'm looking at the position of the top of the ladder, so position of the top of the ladder, that's also a function of time. Okay, so again, that means there's a formula for the position of the top that involves t's. If you plug in a number to that position function, it'll tell you the position of the top at that time. If you take the derivative of the position of the top, that will tell you the rate of change of the top, or how fast the top is sliding down. But you can only know how fast it's sliding down if you plug in a number for t. You understand, as this point goes down, maybe it starts off moving slow, then it moves faster, or maybe the other way around. So when I say, what's the rate of change, you have to tell me, well, when do you want to know it? If I say, what's the speed of the top? You go, okay, fine. When do you want to know the speed? At time 1 second, at time 3 seconds? And then you plug in the number, and then you can get the speed at that point. So position of the bottom, the position of the top are both functions of time. And again, in a related rate problem, those functions are not going to be known. But just because they're not known doesn't mean there isn't a formula for it. Okay, we'll watch the animation one more time. And as you see, it's sliding down, and this point ended up here, and this point ended up over here. Yeah. Okay. Okay, so just to summarize a couple of things I've been talking about as far as functions of time go. When a quantity is changing, that quantity is a function of time. So I'm talking about something like a height. Okay, if you remember, we did that palm tree one. So for example, remember EG stands for example, the height of the palm tree. That would be h of t. It's some function of time. Okay, and what does it mean if it's a function of time? It means there's a formula for that quantity that has t's in it. We may or may not know the formula, and most of the time we don't know the formula. So that's why I'm writing h of t instead of just h there, just to emphasize there's a formula with t's in it. So for example, it could be, and again, I'm just making this up, I have no idea what the height of the palm tree is. The formula could be 2t plus t cubed, some formula. Okay, what else does this mean? Remember, when you have a formula for the height, or when anything is a function of time and you have the formula for it, you don't know anything about the height until you plug in a number. So it also means that we have this function whose inputs are time and the outputs are the number we want, in this case the height. So in my example, I mean the height. So if you want to know the height of the palm tree, you got to plug in a number for t first. Plug the number for t in, and the output will be the height at that time. At that time. Okay. So that's what it means as far as being a function of time. But then the derivative tells you something also. So the derivative of the function tells you the rate of change of the quantity. But in other words, how fast is the thing increasing or decreasing? How fast is the height of the palm tree increasing or decreasing if it's shrinking for some reason? When you're blowing up a balloon, how fast is the volume increasing? How fast is the radius increasing? How fast is the surface area increasing or decreasing if it was being deflated? And also for the latter one, we had 2 different points, so 2 different position functions. You know, how fast is this position changing? How fast is that other position changing? And a lot of times you could think of it as a speed. When it comes to position, the derivative is going to be a velocity or like a speed. But in general, the derivative tells you the rate of change. How is the thing changing? But you have to plug in a number for t first. That's very important. You have to plug a number for t in first, and then you can find how fast the thing is changing at that time. So if we were thinking about the height, if we go back to the height one, okay, so if you take the derivative of the height, it's the rate of change of the height. how fast is the height increasing or decreasing, but you have to plug a number for t in first. So if you plug a number for t in, then the output will tell you, let's go ahead and write speed. The speed of the top at that time, if we're talking about the palm tree example. Or how fast is the top growing, if you want to say it that way. How fast is the quantity changing, whatever the quantity is. So how fast is the height changing at that time? Also, if the quantity is getting larger, if the height's getting larger, if the volume is getting larger, or if the position of something is getting larger, then when you plug a number to the derivative, you're going to get a positive answer. So this is the derivative with a number for t plugged in. You got to plug in a number. It's positive. Okay. If the quantity is getting smaller, then the derivative is going to be negative when you plug in a number for t. Okay, so that's my little story on functions of time. And now let's go ahead and finally talk about the topic for these two videos, rates, related rates. What does that mean? So rates and related rates. Okay, rate means how fast is something changing. In a math class, there's really two different meanings of the word rate. One could be a percentage. Sometimes in other math classes, not in this one, but they'll say, what is the interest rate or something like that, where it's a percentage. So, or it's a speed. Maybe I'll just put speed in quotation marks, which means how fast is something changing. If we're talking about a position, which oftentimes we are, then how fast is this position changing? That's going to be the velocity. Or if you're not worried so much about direction, then it's the speed. Otherwise, if it's a quantity like volume or surface area, then the rate's just how fast is that thing changing. And when it says related rates, what's going to happen is you're going to have an example where two different things are changing. So that means we have two rates, two speeds. And in the problems, what's going to happen is they're going to give you one of the speeds and ask you to find the other one. That's why it's called related rates. If I tell you the speed of part of the thing, or how fast part of the thing is changing, tell me how fast something else is changing. Tell me the speed of the other part. Okay, back to this skateboard example. So one more time, someone is taking the skateboard and pushing it to the right. And now what I'm going to do is, I'm going to put a speedometer on the right end of the skateboard. So speedometer is measuring the speed of this point as it moves that way. Don't look at the reading on the speedometer, because that's just, you know, the picture has the readings all like that, but it doesn't matter. We're attaching a speedometer to that end. It tells me the speed of this point. Then I'm going to attach a speedometer on the other end. And this speedometer is going to tell me the speed of this point. So this point's moving this way, and this point's also moving this way. So we're going to push the skateboard, and it just goes. Sorry, my arrows didn't go with it. And now let's suppose that I stop that movie somewhere in the middle. So let's say here. Okay, so remember, this is just a paused portion of the skateboard, but the skateboard is moving this way. Okay, this point is moving to the right. This point is also moving to the right. And now my question for you is this. Let's say this speedometer reads 3 miles per hour. I know it looks like it's not moving, but I paused the video, so it was moving the whole time. And then you just take a glance at that speedometer and it says 3 miles per hour. My question now is, what is this speedometer going to say? Remember, this speedometer here measures the speed of this point. So at the moment that we paused the video, this point was moving to the right at 3 miles per hour at a specific time. Notice they didn't give me the time. It's at a specific time where I paused the video. So the speed of this point is 3 miles per hour to the right. Now what I'm saying is, at that same time, what is the speed of this point? How fast is it moving to the right? Take a couple seconds and think about it, but it should be pretty easy. If you're like, oh my God, that's really easy. Yes, it is. I'm giving you a really easy example to start here. Okay, well, the answer is that this should also say 3 miles per hour, right? Because those 2 points are attached to the skateboard, you know, so if this end is going 3 miles per hour, so is this one. If it wasn't, if this point was going slower than 3 miles per hour, then the skateboard would have been stretching or something like that. And if this one was going faster than 3 miles per hour, then it was like compressing or something. So it's a rigid object, right? You know, so if this point here is going 3 miles per hour, this point here is also going 3 miles per hour. Those are related rates. I'm starting off with a real easy example, but that's the idea. If you know this, what is this one? If you know the speed of this point, can you tell me the speed of this point? That's the idea. Okay, but again, that one was really easy. They're attached, they're both sturdily attached to the skateboard, so obviously those two rates are going to be the same. Okay, let me give you a more complicated one. Back to the ladder. So one more time, we have 2 points here. We have this point here that's going to be moving to the right. Remember, it's attached to the floor the whole time. Or, I mean, it stays in contact with the floor the entire time. And we have this point here that's going to be sliding down. Okay, let's go and watch the animation again. Sorry, again, my arrows don't go with it, but you see the bottom of the ladder, or maybe you don't see it, but pretend the bottom of the ladder is moving to the right the entire time and staying in contact with the floor the entire time. And the top of the ladder is staying in contact with the wall the entire time. Okay, so what I'm going to do now is I'm going to pretend we pause the video somewhere in the middle. Let's say this is somewhere in the middle as it's sliding down. I'm going to attach a speedometer to the bottom end of the ladder and to the top end. And we have these two speedometers here. Imagine this speedometer here measures the speed of this point as it moves to the right. This speedometer here measures the speed of this point as it moves down. Okay, so my question now is, if this speedometer here reads 5 miles per hour, what is this one going to read? Again, it's a related rate. So before you even try to come up with an answer, let me make sure you understand. I just want you to understand what a related rates means. I'm giving you the rate. Remember, rate is how something is changing, or in this case, the speed. What is the speed? I'm telling you the speed of this point as it moves to the right. And now this one must be related to it because they're attached by this ladder here. So that's a related rate. I want to know what's the speed of this point as it moves down now. Okay, I give you one speed, ask you for another speed. Okay, those are both rates, so they're related rates. Or I can give you how fast one quantity is changing, and you tell me how fast another quantity is changing. Okay, if you're struggling trying to figure out what this top answer is, I get it. It's hard. It's much harder than the skateboard example. So we'll come back to it. We're actually going to do a problem like this. You're going to see that it's going to depend on other things. It's going to depend on what this distance is, what this distance is. Okay, so if I just said, this reads 5 miles per hour, what does this read? You can't answer the question. But if I say this is 5 miles per hour and this distance right here is, 8 feet or something, then you'll be able to answer this question. I know that's not obvious, but you'll see when we do the problem how it works. Okay, one more example so we can again talk about related rates. Back to blowing up the balloon. So again, we have this balloon. The volume is increasing, the surface area is increasing, the radius is increasing. Let's not worry about surface area for right now. But the point is that, okay, let's go ahead and watch the animation real quick. So the balloon is blowing up, so the volume is increasing. At the same time, the radius is increasing. When it comes to the radius, you can think of, when I say how is the radius increasing, how is it changing, you can just think of the speed of the end over here. You draw the radius in such a way that this end is fixed, then I kind of want to know what's the speed of this. But when it comes to the volume, it's hard to think of it as a speed, but still we're going to think of it as it's changing. So when we change one, you change the other. So the volume is changing, and because the volume is changing, the radius is changing. They're related to each other. So that means if you tell me this, let's call it the speed of the volume, really the right way to say it is how the volume is changing. So if this is given, then what I want to know is what's the speed of the radius. Remember, speed is like how something is changing, like the rate of change. So I tell you how the volume is changing, and they're connected because they're, the volume and the radius are related by the fact that they're all part of this balloon here. Then can you tell me how fast the radius is changing? That's a related rate. And in that animation, you saw that the balloon was getting blown up kind of slowly, so the radius was increasing kind of slowly. If you look at a faster animation, see it blew up much faster. Now the speed of the volume, if you want, or how the volume is changing much faster. It's getting bigger much faster. So what's going on with the radius? And the radius is getting bigger much faster as well. They're connected somehow. These two speeds, these two rates are connected somehow. Okay, so that's the idea. So a rate of change is how fast the quantity is changing. And in these related rate problems, we're going to have two of them changing. So you're going to have two quantities changing. These two quantities are changing, but they're somehow connected to each other. They're connected to each other because they're both on a skateboard, both on a ladder. They're both part of a balloon being blown up. Somehow they're connected to each other. So then the rate of change of each quantity, they're related. So those are called related rates. In other words, what I'm going to give you, let me see, is that the next thing here? Yeah. So what's going to happen in a related rate problem is I'm going to tell you how fast one quantity is changing. So the rate of change of one quantity at a specific time, that's important. It has to be at a specific time because remember, at different times, these quantities can change at different speeds. But I'm going to say at this time, when I say at this time, it's kind of like I pause the movie. And at that time, I'm going to tell you the rate of change or the speed of one quantity. And I'm going to ask you to find the rate of change or the speed of the other quantity. And it's going to be at that same time. There's going to be some time going on. I'm never going to give you the time. I'm not going to say at time 5 seconds, but you can pretend it's at time 5 seconds. At some specific time that I never tell you. Okay. Yeah, so it says that here again. Remember that all of this is happening at a specific time. Okay, so when I say rate of change, if I say the rate of change of the volume is whatever, and I give you a number, I'm talking about at a specific time. And then I'm going to say at that time, what is the rate of change of the radius? Or the rate of change of this end of the ladder is whatever. Whenever I say that, I'm saying at a specific time that's happening. What is the rate of change of this other part of the ladder at that specific time? Okay, guys, so I hope at least in this video you're able to understand a few things, some preliminary stuff, of course, and what does related rate mean? Also, what does a function of time mean? What does a derivative mean? There's a lot of things, actually, in this video. Make sure you guys all understand that, and then you can go to the next video where I actually solve some of these problems.